Right. Gonna quickly go through the test. So 1 is F, C, and D. 2 is C. 3 is also C. 4 is D. 5 is D. And 6 is B. For the energy level diagram, so A is your initial reactants, B is the activated complex, and C is your final products. So the next one, so if you're given the elementary steps of the reaction, how do we identify rate determining? It's simply the slowest one. Whichever one of the elementary steps is the slowest is rate determining. For the equilibrium constant expression, you got that. Remember those solids, the iron and the iron oxide, don't stay in. So Le Chatelier's principle, basically, if we've got a system at equilibrium, we can put a stress on it, and it's going to shift the equilibrium. And so you can use Le Chatelier's principle to predict how it's going to shift. All right, so we had a gas stoichiometry problem here. The first thing that we need to do was balance the equation, because it wasn't balanced. Now, as it turns out, if you didn't balance this, it actually would not have changed your answer, just because of the way things worked out. But anyway, so we've got 12.6 liters of hydrogen sulfide. It reacts completely, 3.25 atmosphere and 542 Kelvin. So we want to know how many grams of water vapor will be produced. So the first thing is we do a stoichiometric ratio between the hydrogen sulfide and the water. Now this is what I mean. So they're both 2. So when you do that, so your 12.6 liters of hydrogen sulfide, and for every 2 liters of hydrogen sulfide, you get 2 liters of water. So hydrogen sulfide comes out. But this is 2 over 2, so we multiply by 2, and then we divide by 2, and we get 12.6 liters water. And then we can put that into our ideal gas law. Anytime we need to do grams, we know we're dealing with moles. Remember, you can throw the molar mass in there. For me personally, I think it's easier to do it afterwards, but either way. So we solve for N. And then we just need to put in what we know. So it gives us our pressure, 3.25 atmosphere. Our volume, right there. R we get from the front of the test. We just have to pick the right value, which in this case is this, because we are in atmosphere. And our temperature gives us 542 Kelvin. All of those cancel out. We're left with moles, which is what we want. Do that, and 0.920 mole. And then We just have to convert that into grams. And we know that in 1 mole of water, we have 18.015 grams. Okay. The next one was molarity calculations. So we're starting with 50 grams of sodium chloride. We have to convert that to moles. 8.443 grams in 1 mole. And then you can actually throw it right in here because we have moles. Molarity is moles per liter. And 0.19 molar. For the predict the precipitate, remember we need to compare QSP and KSP. It gives us KSP, we need to figure out what QSP is. Now for this one, it helps because it gives us the KSP is for the silver sulfate. So we know that we're dealing with this. Is solid because we're dissolving. We get this. So our QSP equal to concentration of our silver ions squared times the concentration of our sulfate ions. So where do we get those numbers? Well, it tells us that we have equal volumes of 0.25 molar potassium sulfate and 0.010 molar silver nitrate. So we take that 0.25 and 0.010, but remember, we're mixing them so the volume changes, which changes the concentration. But since we have equal volumes, we just have to divide them in half. So our silver comes from the silver nitrate. So we have that squared times that. When we do that math, what we get is 3.13 times 10 to the minus 6. You know that KSP, which was given to us, 1.2 times 10 to the minus 5th. Because it's minus 5th to minus 6th, KSP is bigger. We will not get a precipitate. So it gives us this reaction. If you decrease the volume, remember decreasing the volume increases the pressure, which drives the reaction to the side with fewer moles of gas, which is going to be to the left, the phosphorus pentachloride. If you cool the reaction, now it says it's exothermic, which means we can treat heat as a product. And if we cool the reaction, it means we're taking away heat. If you take away a product, it moves towards the product or towards the right. If you add chlorine gas, well, chlorine is a product. If you add something, it moves away from it. So it's going to move back to the left. And adding phosphorus pentachloride gas, just the opposite. We're adding the reactant, so it moves it to the right. So here we have the new freezing point. Now I'll point out, I chose a ridiculous amount of salt, so much so that you actually wouldn't be able to dissolve that much salt. It wouldn't work. To get to get a 15.5 mole solution of sodium chloride, you would have to dissolve over 900 grams in 1 kilogram of water, and it just won't do that. In fact, pretty much, yeah, you really can't get anything more than 400, and that's even at high temperatures where the solubility increases. So we're more than twice the amount of salt that you ever could dissolve. That doesn't really matter for the problem. You can still do the math. But I just wanted to point out that you would never see this in real life because it can't happen. Anyway, so we know that the change in freezing temperature is equal to our constant times the molality of particles. Okay. And remember, the molality of particles, we have sodium chloride. We're going to get 2 particles for every mole, which means we take our 15.5 multiplied by 2. So the molality of particles is actually 31. Okay. All right. So at that point, it tells us that our case of F is 1.86 degrees Celsius for molality times that. This cancels out, which gives us degrees Celsius. If we do this, we get 57.66 degrees Celsius. But we need to know the new freezing temperature, so we subtract that from 0, which is just negative 57.66 degrees Celsius. Once again, that could never happen in real life, but you can do the math. Then we have this dilution. We have the 10 molar stock solution of the sulfuric acid, and we want to make a 0.635 molar solution. We need 2.5 liters of it. But we use this, M1, B1, M2, B2. So we're looking for the volume of our stock solution. So what we want is this. Okay. So our initial concentration, M1, is 10. Our desired concentration, M2. Okay, so those units are going to cancel out. And how much of our desired concentration we want. We do the math. We get that. A catalyst is something that will speed up a reaction, but it's not actually used up in the reaction. That's what we're looking for. It speeds the reaction and is not consumed by the reaction. Pressure of a fixed volume of neon gas at 37 degrees Celsius. It has a pressure of 6.5 kilopascals at 0 degrees Celsius. Okay, so we can find our combined gas law on the front. Combined gas law it's a fixed volume, so we get rid of this. And now we just need to figure out what we're solving for, okay? And we're looking for pressure. We can do either P1 or P2, either way. We'll use P2. So P1 times T2 divided by T1 equals P2. We just need to fill in what we know. So P1, 6.5 kilopascal. T2 okay, our new temperature. So it's 37 degrees Celsius, but we've got to use Kelvin, okay? So 37 degrees Celsius is 310 Kelvin. And then T1 is 0 degrees Celsius, or 273 Kelvin. Kelvins cancel out. We're just left with pressure, which is what we want. And we get 7.4 kilopascal. Collision theory. Basically, atoms and molecules have to collide with the right orientation and the right amount of energy in order to react. And then the extra credit. Basically, this was actually on your study guide, the extra credit. It said, be able to use Henry's law, but we really didn't talk about it in class. So I figured it would be worth throwing in for extra credit. So we have S1 over P1 equals S2 over P2. So S stands for solubility. So our S1, we have 0.85 grams per liter. Okay, because it says we can get 0.85 grams of a gas at 4 atmosphere dissolving in 1 liter at 25 degrees Celsius. How much will dissolve in 1 liter at 1 atmosphere, okay, at the same temperature. So our solubility 1, 0.85 grams per liter. Our pressure 1 is 4 atmosphere. Okay. And we know our second pressure, so we're going to bring that over here, 1 atmosphere. And that's going to give us our second solubility. Atmosphere cancels out. And we get S2 equals 0.21.
Dang, I'm kind of amazed that I got that right.
All right. So there is extra credit. It's posted on LMS. Basically, it's dealing with equilibrium and how equilibrium can affect hemoglobin, which carries oxygen at higher elevations. So you can find information on this in the book, but you can also just find it online. That's acceptable too. So basically, just a short report about equilibrium and hemoglobin. So, like I said, the exact details are on LMS. So, okay. Well then, let's move on into some new material. This next chapter, it's actually one of my favorites. We are going to move into chapter 18, which is all about acids and bases. Acids and bases. So, just as a, I guess, explanation, I don't know, maybe that's not the right word for it, but base is it's the word that we use in the United States. If you ever hear a British scientist or somebody who has learned British English talking about it, instead of base, they will use alkaline. Same thing, just two different words. Okay? It's another one of those things where United States and England just have a different word for the same thing. So, but because we're here in the United States and I was taught chemistry in the United States, you'll hear me say acids and bases. So anyway. Now, when you hear the word acid, a lot of times what you will think of is sort of the Hollywood version of acid, where somebody gets acid and it touches their skin and they start to melt away. And are there acids that can do that? Sure. Are most of them not nearly that exciting? Yes. In fact, a lot of the food and drink that we put into our body has acids.
Isn't like Gatorade super bad for your teeth because it's like higher acidic than most drinks?
I would say more the sugar is what's the problem. Now it does come down to acid because when the bacteria eat the sugar, they make acid. So it's not as much that it has acid in it as much as the sugar is metabolized by bacteria into acid. So there's just an extra step there. But yeah, sugary drinks are definitely hard on your teeth, for sure. So, but yeah, like a lot of our food has acids in them. If you eat any sort of citrus, so like oranges, lemons, things like that, they've got a bunch of acid in it. Okay? They just do. In fact, acid often is what produces a sour taste. So that's why a lot of citric, or a lot of citrus fruits have acid. They're sour. Now, base, we don't really eat a lot of bases because bases tend to taste bitter, and so it's not a very pleasant thing to eat. Bases actually feel slippery on your hand as well. Soap is largely a base, and so it feels slippery. So, some properties of them. Acids and bases actually tend to conduct electricity because we have, well, electrolytes. They're and you'll see why we have electrolytes, but you definitely will see them. Chemical properties, reactions with litmus. I'll show you some litmus paper and what it works or how it works. I don't have it set up today, but we'll show you what happens. But basically, litmus is something that will tell us if we're dealing with an acid or a base. Red litmus is that will tell us it's acid. So if you dip the paper and it comes out red, you have an acid. If you dip the paper and it comes out blue, we have a base. Like I said, I'll show that to you here. Hopefully next time. Just kind of depends. Well, depends if I remember to get it set up. So, reactions with metals. Metals react with acids quite easily. Now, different metals will react differently. Some react very, very quickly, others very slowly. But metals tend to react with acids. pure metals don't react with bases nearly so much. However, if you have a carbonate, like calcium carbonate, which is limestone, we can get some reaction there. Still, it's much more likely to react with the base or the acid. So anyway, so let's talk about what is an acid and what is a base. And what we're going to see all the time throughout this chapter, H plus, OH minus. Okay. H plus and OH minus. Now H plus is a hydrogen atom that has lost its electron. And really that just leaves a proton. So we will often use that term sort of interchangeably, proton, hydrogen ion. It's a little bit more accurate to say hydrogen ion because sometimes hydrogen has one or two neutrons with it, but the vast majority of them don't. So we can use proton pretty interchangeably. And then OH minus, that is hydroxide. That one will pretty much always just be hydroxide. That's what we call it. So, and if we want to determine if something is an acid or a base, we measure the ratio between these. Okay. We want to know, does it have more of these protons or more of the hydroxide ions? If it has more of the protons, it is acidic. It's an acid. If, however, it has more of the hydroxide, it's a base. And that's really what it comes down to. When we measure whether something is an acid or a base, we're looking at these concentrations, and we want to know where we have more. Okay. So, all right. Now, as a side note, sometimes what you will see written instead of just the H plus, the H3O plus. Whenever we're dealing with acids and bases, at least for this class, we're always going to have them in water. We're dealing with an aqueous solution. And so what can happen, and what does happen really, is this is actually going to latch on to one of the hydrogen, or one of the water molecules, and we form this. They're the same. Okay, whenever we're dealing with acids and bases, if you see one of these, it's the same thing. So, okay. Now, speaking of water, water can spontaneously break apart. Like this. Now, if you have pure water, remember, anytime it breaks apart, you get one of each. So we're never going to have more of one than the other. And that's why pure water we consider to be neutral. It's not an acid, it's not a base, because anytime it breaks apart, we get one of each, and so neither one is going to have more than the other. So, anyway. Okay. so the question of, how do we, what is an acid, what is a base, is a question that, people were trying to figure out for a long time. Or, at least they started a long time ago. The first person to really come up with a good way of describing it was a Swedish chemist by the name of Arrhenius. And so we have the Arrhenius model. Okay. And basically, what the Arrhenius model says is anything is an acid if it has a hydrogen that can pop off. Okay. So anything that has a hydrogen that's able to jump off and come into solution is an acid. So for example, this is one that we'll work with in the lab actually, hydrochloric acid. What can happen is this. They break apart, we get the H plus. Okay. So that is basically what Arrhenius said was an acid. Now on the other side, we had to have what is a base. And well, acids provide this proton, an Arrhenius base provides BOH minus. Okay. And that works. Okay, it works pretty darn well. It makes sense. Okay, if we need more of these hydrogen ions in order to be an acid, well, we need something that's going to give hydrogen ions. We need more of these hydroxide ions. We need something that's going to give the hydroxide ions. Okay. Anyway, so that's the Arrhenius model. Like I said, it works really, really well, but it's not perfect. Okay. Because, well, we've got this pesky little compound called ammonia. Now, looking at that, it looks like, well, it's an acid, right? We can pop that hydrogen off. Well, as it turns out, ammonia is actually a base. And so, since, the Arrhenius model, like you said, it works pretty darn well, but we needed to expand on it. And so, we now have two scientists that came a little bit later that refined the model of what is an acid and what is a base. So we call this the Bronsted-Lowry model. Okay. And this is all based off of hydrogen. Okay. So we've gotten rid of the whole, we need to provide the hydroxide. Okay. And so to be honest, an Arrhenius acid and a Bronsted-Lowry acid are both really pretty much the same thing. Okay, a Bronsted-Lowry acid, we need to be able to give this hydrogen ion. But the difference is a Bronsted-Lowry base is able to accept the hydrogen ion. And that's what happens here. Okay, so this actually, when you mix it with water, what happens is one of these hydrogens pulls off onto this, which leaves the OH minus. Okay. So the Bronsted-Lowry acid is able to take the hydrogen off of water, which leaves our OH minus. That's where our increased concentrations of OH minus come from. It's from the water, because our Bronsted-Lowry base right here took the proton. Okay. Now this also brings up an interesting concept. So remember we said that the Bronsted-Lowry acid was able to give a proton. Well, what's giving the proton is this. Okay, so water is acting as an acid. But notice we have the double arrow. This is an equilibrium situation. This is reversible. So what can happen is a proton can leave this and join that. So now, since that is donating the proton, this is now the acid, and this is accepting the proton, so it's the base. Okay. And so what happens, we get these pairs. This was a base, and it becomes an acid. We call this the conjugate acid. Okay. And these pair up. This is the conjugate base. So whatever started as an acid, at the end becomes a conjugate base. Whatever started as a base, at the end becomes a conjugate acid. Okay. So we get these pairs. So the Bronsted-Lowry model is able to explain why ammonia is a base, even though it doesn't have that hydroxide ion in order to donate. Okay. Now, at this point, we want to point out sometimes we can have what we call polyprotic acids. So if we have phosphoric acid, this is definitely a acid, okay, and it can lose this hydrogen. So what we get is H plus, H2, CO4 minus. Now, as it turns out, now this obviously is a base. Okay, this is the conjugate base. But it turns out this actually can be an acid too. So we could lose another hydrogen ion. Okay. So once again, acid, we've lost it. This is a base. But that's also an acid. So we can have multiple hydrogens that come off. Right? And it will follow this pattern. All of this is going to go to this before any of this goes to that. And then similarly, all of this has to happen before any comes and does that. The reason for that will be more evident in future classes. It has to do with K and A values. So, anyway. And that works really, really, really well. Once again, it's not perfect. We do have a couple of things that act as acids and bases that are not fully explained by the Bronsted-Lowry model. For those, we go to what's called the Lewis model, and that deals with electron pairs, electron pair donors and electron pair acceptors. To be honest, we're not really going to do much with Lewis acids and bases in this class because they're less common. Okay? And they're out there. I'm not saying they're not important, but for our class, if you can understand the Bronsted-Lowry model, that's going to be just fine. And the way it works, really, so we started with Arrhenius, and that worked pretty darn well. But we needed more. So we went to the Bronsted-Lowry model. Now, anything that is an Arrhenius acid or an Arrhenius base is also a Bronsted-Lowry acid or a Bronsted-Lowry base. It works really well because we took everything that was already acid and base. We said, okay, our model works for that plus some. The same thing is true of Lewis. Okay, so anything that is a Bronsted-Lowry acid or base is also a Lewis acid or base. Okay. But like I said, Lewis deals with anything that is a Lewis acid or base but not Bronsted-Lowry is less common, and we're not really going to deal with it so much in this class. We're going to focus on whether or not something can donate a hydrogen or accept a hydrogen. And that's where we will, that's the level that we're going to keep it at, just for simplicity. So basically, that's what we're going to be dealing with through this entire chapter. Okay? We're going to be saying, does this solution have more hydrogen ions or more hydroxide ions? More hydrogen ions, acid. More hydroxide ions, base. Okay? And then we're going to look and say, okay, why? Why are we breaking apart this water? Okay? Or why are we generating these hydrogen ions or hydroxide ions separately? Okay? And is it that something is, you mix it with water and all of a sudden the water would rather have that extra hydrogen than whatever you've mixed with it? Or is it that whatever you put into the water would rather have that hydrogen ion than the water molecule itself? And so that's sort of what we have with acids and bases. So, and that's the end of section 1. basically, we just want to establish what is an acid or a base. We're going to do a lot more work with them. Like I said, this is our first time that we're really going to go and do a lab. So we'll be working with acids and bases. There's a technique called titration that will allow us to determine the concentration of, well, you can go either way, either concentration of an acid or the concentration of a base. I tend to do it so that we know the concentration of a base and figure out the concentration of the acid. But yeah, so we'll do that, and we'll have we'll talk about the interaction between acids and bases. So, but that is it for today. So we'll stop there, and obviously we have a little bit of homework. So we are moving into chapter 18, and it is these